How do you apply Dirac notation to spin systems? Imagine trying to describe the tiny magnetic compass inside an electron. How do we write its orientation in a way that makes sense in quantum mechanics? That's where Dirac notation comes in. In quantum physics, we use special symbols called qubits to representing the state of a particle's spin. For a spin 1/2 particle, like an electron, the main states are written as up 4 spin up and down 4 spin down. These are like the two basic positions of a tiny magnet. These states are orthogonal, meaning they are completely different, and they form a simple basis for describing any spin state. Any spin state can be written as a combination of these two basis states. For example, if you have a state psi, it can be written as a sum of alpha up plus beta down, where alpha and beta are complex numbers. These numbers tell us the likelihood of measuring the spin as up or down. The sum of the squares of their magnitudes always equals 1, which keeps the total probability at 1. Operators are used to measure or change the spin. For example, the spin along the z-axis is represented by an operator called sz. When sz acts on up, it gives back the same state multiplied by a number, which is the eigenvalue. For up, that value is plus half the reduced Planck constant. Similarly, for down, it gives minus half the reduced Planck constant. These eigenstates are special because they give definite measurement results. Ladder operators, called s plus and s minus, help us move between these states. S plus turns down into up, and s minus does the opposite. They are useful for calculating how spins change or transition from one state to another. These operators are not Hermitian, which means they are not equal to their own conjugate transpose, but they are essential for understanding spin flips. To find the average value of a spin component in a certain state, we use the bracket notation. The expectation value is written as psi s psi, where psi is the bra or the conjugate transpose of psi. To find the chance of measuring the spin in a particular state, like up, when the system is in psi, we calculate the inner product up psi and take its magnitude squared. When dealing with particles that have both position and spin, we combine the two descriptions into a spinor. This is a more complex state that includes the spatial wave function and the spin part. It looks like a column of two functions, one for spin up and one for spin down, each depending on position. This helps describe situations like entangled particles, where spin and position are linked. Using Dirac notation for spin systems is vital in quantum computing. Qubits are often just spins of electrons or nuclei. This notation makes it easier to describe quantum gates, measurements, and entanglement. It simplifies calculations and helps us understand how spins behave in devices like quantum sensors or magnetic resonance machines. In essence, applying Dirac notation to spin systems means representing the two basic spin states as vectors, using operators to measure and manipulate these states, and calculating probabilities with inner products. This approach forms the foundation for controlling and understanding spin-based quantum technologies.